Good evening, students. Today's our topic is Laplace Transform. So let's start our discussion about Laplace transform. Actually, this transformation is meant with, or it actually deals with our circuit theory or network analysis part. Actually, whenever we give a voltage response to an electrical circuit, as we know that circuit gives us a current and that is the response of the circuit. It can be viewed as inversely also, that a current response is given in the input end and a voltage is in the output part. So there may be either of the two cases, that is, we can give that current as response or we can give voltage as response. Now, to get the output value from the input or the given input signal, we have to apply some linear equations. Now, sometimes it becomes tedious to solve those equations what we are getting from our applying or our application of KVL or KCL. Now, here comes the integral differential equations such as these type of transformations, that is the Laplace transformations. Actually, from the Laplace transformations, we get the output values in which the steady state value as well as the transient response of the circuit is also given. Now, let's skip that part of the discussion, and in this particular class, I am actually want to give you the salient features of this transformation, how these transformations have been taken place, or what are the properties of the Laplace transformation, as because it is also an important topic for your mathematical physics part. So let's begin the topic, that is Laplace transformation. Now, any input value or any function, if it is given as a function of time, that is f of t, by Laplace transformation, actually we can convert this function, that is the time function, into its frequency domain. So we can write that Laplace transformation of function of t, that is the time function. So Laplace transform of the time function actually gives us the frequency, the function in its frequency domain, or it is given as capital F of s. Now, how can you transform this function ft to fs? Now, that is mathematically Laplace transform of ft. Actually, it is given as integral 0 to infinity f of t, that is the function itself, e to the power minus st dt. So this is the integral formula, or this is the formula which we have to apply to get a function in its frequency domain. So this gives us the function fs, that is the function which is actually transformed by applying Laplace transformation from its time domain to the frequency domain. This is the only formula which we are going to apply for the Laplace transformation. I think all of you get it. So let's move on to how we can apply, or let us move on to discuss some transformations or Laplace transformations of some very important or basic mathematical functions. First of all, I am taking a function which is known as unit step function. Unit step function. As the function, by its name, it actually gives us the idea that the function, the mathematical form or the graphical form must be this. That is, this is the f of t. Now this is the time axis and this is the function value, and since the function is known as unit step function, that means the function has f of t, that is the value of the function is f of t equals to 1 whenever time t greater than equals to 0, else it is 0 when t less than 0. So this is the mathematical form or mathematical expression of a unit step function, and the graphical representation is given here. This is the value 1. Now we are going to transform, or we are going to apply Laplace transformation of this unit step function. So Laplace transform of f of t, as I have discussed earlier, that the value should be integral 0 to infinity f of t e to the power minus of st dt. Just remember this integral value or the integration, the formula of the integration, that is now putting the value of f of t. So when t greater than equals to 0, now my function, my limit of the integration is from 0 to infinity. So actually this is the range at which the time t greater than equals to 0. So in this region, this f of t for unit step function, the value of f of t is 1. So just I am putting the value of 1 here, and then e to the power minus st dt. So it becomes e to the power minus st by minus s, and the limit 0 to infinity. Now this is minus of 1 by s e to the power minus infinity. Now what is the value of e to the power minus infinity? I know that all of you must know the value, that e to the power minus infinity is actually can be expressed as 1 by e to the power infinity, and 1 by e to the power infinity means infinity. Now 1 by infinity means 0. So e to the power minus infinity becomes 0, and then minus of e to the power 0. So this will be minus 1 by s, 0 minus 1. So the value, final value is 1 by s. So this is the Laplace transformation, or the value of the unit step function, or the value of the Laplace transformation of unit step function. It is equals to 1 by s. Okay. Now let's move on to a next function. So the value of unit step function f of t equals to 1 by s. Now my second function, let us consider an exponential function e to the power alpha t or e to the power at. So now let's consider another function number 2 equals to e to the power, that is f of t equals to e to the power at. So this is the second function e to the power at. Now Laplace transform of e to the power at. So again writing the formula, integral 0 to infinity f of t, that is e to the power at into e to the power minus of st dt. Okay. Now here you have to remember one thing, that whenever this type of exponential values, that is two functions, both of them are exponential, then you have to write first of all the s part, the frequency part. So you have to actually write it as e to the power minus of s minus a t dt. Just remember this thing only, that you have to write the frequency part or the s part initially or firstly. Now then the integration value, that is the integral, that is e to the power minus of s minus a t, and that is 1 by s minus a with a negative sign. Put the value of the limits as 0 to infinity, so it becomes minus 1 by s minus a. Again e to the power minus infinity, so it becomes 0, then minus of e to the power 0, that is 1, so the value is 1 by s minus a. So this is the Laplace transformation of e to the power at, that is 1 by s minus a. Okay, have you got it? Just comment here. Okay, fine. So let's move on to our third function, that is f of t equals to e to the power minus of at. So let's move on to the third function, that is e to the power minus of at. So now the function is e to the power minus at, and this is our third function. So Laplace transform of e to the power minus at. So e to the power minus at becomes, this is e to the power minus at dot e to the power minus of st dt. So taking again the frequency part earlier, that is e to the power minus of s plus a into t dt. What happened here? Is it okay? Okay. So here again I am taking the frequency part or the s part initially, and it becomes e to the power minus of s plus a t dt, and then the integration, that is minus of 1 by s plus a e to the power minus of s plus a t, limit 0 to infinity. So it becomes again 1 by s plus a, it is 0 minus of 1, so the value is 1 by s plus a. So you can see that when the function is e to the power at, e to the power at, the Laplace transformation is 1 by s minus a. Whenever the function is e to the power at, the Laplace transform is 1 by s minus a, and when the function becomes e to the power minus of at, then the Laplace transformation is 1 by s plus a. So e to the power at becomes 1 by s minus a, and e to the power minus at becomes 1 by s plus a. I am actually talking about these two values time and again, since because you have to apply or you have to remember these values in circuit theory or in network analysis whenever Laplace transformation goes to whenever you are going to apply these type of transformations. So just remember the values. Whenever the function is e to the power at, the transformation is e to the power the transformation is 1 by s minus a, and whenever the function is e to the power minus at, the transformation is 1 by s plus a. Okay, so let's move on to another function, that is number 4. But before proceeding to number 4, let's check a property of Laplace transformation. That is, now I am going to show you that Laplace transformation of linear combination of functions. That is, if there are two functions f1t and f2t, if there are two functions f1t and f2t, where and a and b are two constants, that is, if I have to transform a of f1t, a of f1t plus b f2t. So if I have to apply Laplace transformation, or if I have to find out the Laplace transformation of these type of functions, that is, there is a linear combination of two functions, a f1t and the other one is b f2t. Now how I can proceed? That this actually, it means that here is, you have to write 0 to infinity. So this is the entire function. So you have to write a f1t plus b f2t. So this is the function itself, and then e to the power minus of st dt. Now splitting this as two integrals, so it can be written as a integral 0 to infinity f1t e to the power minus of st dt plus b integral 0 to infinity f2t e to the power minus of st dt. So here I can write it as summation of two integrals. One is a integral f1t to the power minus st dt, and the other is b f2t integral f2t e to the power minus of st dt. Now actually this is the Laplace transform of, this can be written as Laplace transform of f1t, and this can be written as Laplace transform of f2t. Why? As because the formula of Laplace transformation tells us that the transformation of f1t is actually integral 0 to infinity f1t e to the power minus of st dt. So here I am writing integral 0 to infinity f1t to the power minus st dt as the Laplace transform of f1t and plus b Laplace transform of f2t. So now this property or this principle I am going to apply in our number 4 function. That is, let us consider a hyperbolic function. You know, there are cos hyperbolic, sine hyperbolic, tan hyperbolic. So let's consider a hyperbolic function as our next function, that is function number 4. So let's find out the Laplace transform of cos hyperbolic omega t. So this is function 4, f of t equals to cos hyperbolic omega t. It can be written as, or the problem can be written as sine hyperbolic omega t. Now, as we know that a cos hyperbolic function, that is cos hyperbolic function, can be written as half of e to the power omega t plus e to the power minus of omega t. Cos hyperbolic function can be written as half of e to the power omega t plus e to the power minus omega t, as sine hyperbolic omega t is also, you can write it as sine hyperbolic omega t. Sine hyperbolic function, just I am telling the sine hyperbolic function as because the sum can be given as function of t equals to sine hyperbolic omega t, and sine hyperbolic function is expressed as half of e to the power omega t minus of e to the power minus of omega t. So these are the two functions, cos hyperbolic omega t and sine hyperbolic omega t. Now let's find out the Laplace transformation of cos hyperbolic omega t. Now, so Laplace transform of cos hyperbolic omega t, what I can write it as Laplace transform as half of Laplace transform of e to the power omega t, Laplace transform of e to the power omega t plus, or it can be written as half common, that is Laplace transform of e to the power minus of omega t. Just look at this, that cos, as because cos hyperbolic omega t can be written as half of e to the power omega t plus e to the power minus omega t. That is, cos hyperbolic function is written as the summation of two functions, or the linear combination of f1t and f2t, as just I have explained earlier in the previous part. So whenever we are going to take out, or we are going to find that transformation of cos hyperbolic omega t, it is nothing but you have to find out the Laplace transform of e to the power omega t plus Laplace transform of e to the power minus omega t, and as because cos hyperbolic function has a value of half here, so you have to put that half here. Now, what is the value of Laplace transform of e to the power omega t? In our problem number 2, I have discussed, or I have derived the value of e to the power at, Laplace transform of e to the power at, and you can remember that the value is 1 by s minus a. And I have also derived the value of e to the power minus of at, and the value was 1 by s plus a. So just follow that values, or just putting those values as, so Laplace transform of e to the power omega t becomes 1 by s minus omega, and then e to the power Laplace transform of e to the power minus omega t means the transformation value is 1 by s plus omega. Now just simplifying these values. So this is s square minus omega square, then s plus omega plus s minus omega, that is twice of s, and it becomes, the value becomes s by s square minus omega square. So this is the Laplace transformation. So this is the Laplace transformation of cos hyperbolic omega t, s by s square minus omega square. This is the Laplace transform of e to the power cos hyperbolic omega t. I think all of you are clever enough, or you can derive the another function or the Laplace transform of sine hyperbolic omega t yourself. So just go on proceeding this way. You can find out the Laplace transform of sine hyperbolic omega t, and the value becomes omega by s square minus omega square. You can write it, the value, and after my class, after this live streaming, you can derive the function yourself and find out the value of Laplace transform of sine hyperbolic omega t, and the value is omega by s square minus omega square. So the denominator of cos hyperbolic omega t and sine hyperbolic omega t is equal, but only the numerator changes. Here the numerator is s, and for sine hyperbolic omega t, the numerator becomes omega. Okay, so let's proceed to next function, and this is simple trigonometric function cos omega t or sine omega t, cos omega t or sine omega t. Now again you can write cos omega t or sine omega t as a combination of e to the power j omega t. So now my next function is cos omega t. It can be, I think it is problem number 5 or function, the fifth function, that is cos omega t. Now for cos omega t or for sine omega t, you can write cos omega t equals to half of e to the power j omega t, where j is the complex number, plus e to the power minus of j omega t, as because e to the power j omega t means that is cos omega t plus j sine omega t, and then e to the power minus j omega t means cos omega t minus of j sine omega t. So the value of cos omega t is 1 by 2 or half of e to the power j omega t plus e to the power minus j omega t, as sine omega t can be written as 1 by 2j e to the power j omega t minus of e to the power minus j omega t. So e to the power j omega t means cos omega t plus j sine omega t, then minus of e to the power minus j omega t, it becomes cos omega t cancels out, twice j sine omega t remains there, divided by twice j, so it becomes sine omega t. Now let's move on to the Laplace transformation. Let's find out the Laplace transformation of cos omega t. So here also you can write it as half of Laplace transform of e to the power j omega t plus Laplace transform of e to the power minus of j omega t. And then again e to the power j omega t, e to the power at, Laplace transform of e to the power at means 1 by s minus a. So it becomes 1 by s minus j omega plus 1 by s plus j omega. Then simplifying it as s square minus j square, so that is plus omega square. So the numerator becomes s plus j omega plus s minus j omega. That means we have twice s, and the value becomes s by s square plus omega square. So the Laplace transform of cos omega t. Oh, fine, Shikha. Okay, that's great. Now let's check it out. That Laplace transform of cos omega t becomes s by s square plus omega square. So again you have to find out the value of Laplace transformation of sine omega t. Again, proceeding in the similar manner, you can find out the value of Laplace transformation of sine omega t, and the value becomes omega by s square plus omega square. So you can do it later on. That is Laplace transform of sine omega t, and the value becomes omega by s square plus omega square. Okay? Do you have any problem up to this? Just comment me. Have you any doubts so far? Very good, Papri. Excellent. Excellent going on. So, Satyajit, it's okay. Ankita, Mousumi Ghosh, Rajeshri, Pinky. Okay. Shagorika. Okay. Very fine. So, let's proceed. Now, let's move on to the next function. Now, this is a typical example. It is a time function. Actually, all of these are time functions, but the value is a familiar one, but the value looks like it has some element of fear. Why? Let the function is f of t equals to t to the power n minus 1. So this is the function f of t equals to t to the power n minus 1, where n is a positive integer. Okay? So now Laplace transform of t to the power n minus 1, by applying the formula, you have 0 to infinity t to the power n minus 1 e to the power minus st dt. Now we have two functions, t to the power n minus 1 and e to the power minus of st dt, and e to the power minus st dt, as we all know, that is, it is the exponential function, and whenever we have two types of different functions product and we have to do their integral, we have to apply the integration by parts. So keeping the exponential part as the second function, so t to the power n minus 1 can be regarded as the first function. So first function integral of the second. So keeping the first function integral of the second, that is minus of s e to the power minus st, the limit 0 to infinity, minus differential of the first, that means t to the power differential of t to the power n minus 1. So it becomes n minus 1 t to the power n minus 2, and then integral of the second, from the integration of e to the power minus st, we actually get 1 by s e to the power minus st dt, and here the integration, that is, and the limit again remains the same, that is 0 to infinity. So by applying integration by parts, this is the second step, or this is the next step. Now here, as you can see, that whenever I am putting the value of the limit infinity, it becomes e to the power minus of infinity, and it becomes 0. And then whenever I am putting the lower limit as 0 into t to the power n minus 1, it again gives us 0. So this part gives me 0 value. So just omitting this, so the value becomes n minus 1 by s, that is the second part, n minus 1 by s integral 0 to infinity t to the power n minus 2 e to the power minus of st dt. Okay? So from the Laplace transformation of t to the power n minus 1, just listen carefully, that the Laplace transform of t to the power n minus 1 gives me n minus 1 by s integral 0 to infinity t to the power n minus 2. So by calculating the Laplace transform of t to the power n minus 1, here the first value becomes t to the power n minus 2. So if we go on repeating this process, that is, next time we have to integrate this value, and then we actually get t to the power n minus 3, and then repeating thus, we can say that Laplace transform of t to the power n minus 1, it gives me n minus 1, that is the first term. Then after integrating this part, we must get n minus 2, then n minus 3, and after that 2, 1, and so on, divided by every time a s here 1 by s ki kore elo 1 by s. So the 1 by s comes from the integration of the second function, that is e to the power minus of st. Papri, 1 by s comes from, if you go on integrating by parts, then what is the formula of integrating by parts? That is first function integral of the second minus differential of the first integral of the second and whole integration. So the second part becomes, now the integral of the second becomes, that is e to the power minus of st, means you have minus of 1 by s, and that minus of 1 by s, and here initially there was a negative sign, so they become a product of positive sign, a minus of minus 1 by s, so it becomes 1 by s. Okay? So every time a s arrives here, but carefully you have to so this s becomes s of n minus 1, as because the first integration of t to the power n minus 1 gives me a s, and proceeding in the similar manner, actually it becomes integral of 0 to infinity. So the value of t to the power, the value of t, it actually decreases. Initially it was t to the power n minus 1. After first integration, you get t to the power n minus 2. After second integration, the terms become t to the power n minus 3, so on. So the last term should be t to the power 0. So I am writing here t to the power 0 e to the power minus of st dt. Have you got it? Is it clear to you all? How can I get the Laplace transform of t to the power n minus 1? Actually, this is known as the method of induction in mathematics. So here the last integral will be integral 0 to infinity t to the power 0 e to the power minus st dt, and as you know that t to the power 0 means 1, so e to the power minus st dt means again minus of 1 by s e to the power minus st dt. So the integration value, the final value becomes, I am writing in the top part of the board, that is, so Laplace transform of t to the power n minus 1, it becomes n minus 1, n minus 2, so on after that to 1 s to the power n minus 1, and then minus of 1 by s e to the power minus st, minus of 1 by s e to the power minus of st, and then the limit 0 to infinity, and then the limit 0 to infinity. If you have any problem to see it, as because the logo here in the topmost part of the display, or so I'm writing here again, you may have problem to see. So the value becomes n minus 1, n minus 2, then 2, 1, s to the power n minus 1, and this is minus of 1 by s e to the power minus st, limit becomes 0 to infinity. Okay, now this is the numerator part. You all know that this is factorial n minus 1 into s to the power n minus 1, and then minus of 1 by s, and then by putting infinity, again e to the power minus infinity means 0, and after putting 0, e to the power 0 means 1, so it becomes only 1 by s. So the value becomes factorial of n minus 1 s to the power n. So this is the Laplace transformation of t to the power n minus 1. So the Laplace transform of t to the power n minus 1 is actually factorial n minus 1 divided by s to the power n. If you have any problem in any step of this derivation, please mention. Don't hesitate to mention here. So the value of Laplace transformation of t to the power n minus 1, as I have told you earlier, that it is a very important No, Satyajit, here we could not apply, or we cannot apply gamma function, as because Laplace transformation is something different than gamma function. So we cannot apply gamma function here. Okay. Now, why this transformation of t to the power n minus 1 is important? As because now if the function is simply f of t equals to t. F of t equals to t. Now, what is the Laplace transformation of, if the question comes here, that what is the Laplace transformation of just t? What is the Laplace transformation of t? So, you have to think from this derivation, that for t to the power n minus 1, if the transformation of t to the power n minus 1 is equals to factorial n minus 1 divided by s to the power n, then by putting n equals to, so how you can get here as t? How you can get the function of t? Now just put n equals to 2. If you put n equals to 2, it becomes t to the power 2 minus 1, that is t. So by putting just n equals to 2 here, that is the value will be factorial of 1. Factorial 1 means 1 divided by s square. So the Laplace transform of t to the Laplace transform of t, it actually equals to 1 by s square. And this function, that is f of t equals to t, f of t equals to t, is known as ramped function. It is also an important function in circuit theory or in communication. It can be used everywhere. It is used everywhere, and it is known as the ramp function. So f of t equals to t is actually a very important function, and the Laplace transformation is simple 1 by s square, and the value I have derived from the Laplace transform of t to the power n minus 1, as because n is an integer here. Okay. Now let's move on to transformation of exponentially damped function. Again, it is a very much important type of function for us, that is for physics students, that is exponentially damped functions. So Laplace transform of, let the function is e to the power, e to the power minus at ft. Let the function is e to the power minus at. So here I am going to find out the Laplace transformation of e to the power minus at ft. Again, it is a generalized derivation. Here we can give that ft as anything we wish. It may be a trigonometric function, it may be a hyperbolic function, it may be a simple value, it may be anything. So but this is known as the exponentially damped function. Now, so the first step, again the similar, that is 0 to integral 0 to infinity e to the power minus at, e to the power, write it as f of t, e to the power minus at, e to the power minus st dt. And as I have told you earlier, that you have to follow, or you have to give that s the priority. That is, it should be written as s plus a t dt. Now, if you check this integral value, if you check this integral, it is actually integral 0 to infinity f of t e to the power minus of s plus a t dt. Now what you have to check, why I am telling you that check this integral value, as because whenever I am writing integral 0 to infinity, just follow my words, when I am writing integral 0 to infinity f of t e to the power minus st dt, it becomes f of s, capital F of s. I'm repeating again. Whenever I'm writing integral 0 to infinity f of t e to the power minus st dt, it becomes capital F of s. Right? Now here I'm writing here integral 0 to infinity. Just compare the earlier one, what I'm telling you. That here I am written integral 0 to infinity f of t e to the power minus s plus a t dt. It is similar to e to the power minus s t dt. And there we are writing it as capital F of s. So I'm writing this as capital F of S plus A, isn't it? Have you got it all? So this can be written as capital F of S plus A. Have you got it? Why I am writing it, or why it can be written as capital F of S plus A? Okay, Mrinal, Ankita, Satyajit, Shikha. So anyone, you have any doubt about this? Okay, Brijesh, Papri, Amit Pramanik, fine. So, so here in this way, an exponentially damped function. Okay, Shagorika, an exponentially damped function can be transformed, or can be here we can apply the Laplace transformation as. Now if let's check out some exponentially transformations of some exponentially damped functions. This is actually a general value, as because I have not yet mentioned the value of f of t. So now some examples of exponentially damped function, that is Laplace transform of e to the power minus at cos of omega t. So what I am talking, that you have to find out, you have to find out if you have to find out the original Laplace transformation of the function f of t. Now here f of t is actually cos omega t, and already we have derived the Laplace transform of cos omega t. It was s by s square plus omega square. It was s by s square plus omega square. Now following the previous example, that you can write it as capital F of S plus A, you have to substitute that S by S plus A. So what will be the value of this function? The Laplace transformation of e to the power minus at cos omega t can be written as S is replaced by S plus A, and then also it was S square plus omega square, so it is S plus A whole square plus omega square. So this is the Laplace transformation of e to the power minus at cos omega t. Again, what will be the value of e to the power minus at sine omega t? What will be the value of e to the power minus at sine omega t? Let's see. I'm giving you 1 minute. The clock starts now. Find out the value of e to the power minus at sine omega t. I'm waiting for your response. Find out the Laplace transform of e to the power minus at sine omega t. $20 gone. I'm waiting for the value of Laplace transform of e to the power minus at sine omega t. Papri already responded. Thank you, Papri. Anybody else? Papri said the value is omega plus a divided by s plus a whole square, s plus a whole square plus omega square. Papri said the value is, I'm writing the value of Papri. Papri said it will be omega plus a divided by s plus a whole square, s plus a whole square plus omega square. So this is the value of Papri. Satyajit said that numerator will be changed into omega. Okay, Satyajit is telling that numerator value should be omega. Utpal is telling that its value is omega by s plus a whole square plus b square. Utpal, I can't get it why it is b square. Learn physics through experiments. I'm already checked your YouTube channel, Learn Physics Through Experiments. I seriously find it very exciting. Just go on, post your experiments. I think just now you are very much busy with your exam. So after the exam is over, you may post experiments. So learn physics through experiments. He is giving as omega plus a divided by s plus a whole square plus omega square. Shikha Chaudhary, same sir. What is the same sir? Shikha, Onkita gives me the result as omega by 2, then s plus a whole square plus omega square. Mrinal says that s to change to e, rather he wants to that it is omega. So Utpal again gives me the value as omega by s plus a whole square plus omega square. Okay, so time is up. Thank you all for your attention and for your response. So actually, Papri gives me the first result, but Papri, there is a small error that the value of, okay, Papri answer, okay. Now, but Shika, Papri is a bit wrong. Yes, Ranjit, okay, fine. So Papri is slightly wrong as because here this is the f of t. Okay, this is the f of t, and if you check the value of the Laplace transform of f of t, you find that there the value was omega by s square plus omega square. If the value was omega by s square plus omega square, and here just before this I'm talking about when I'm talking about the Laplace transform of exponentially decaying functions, then I'm telling you that you have to use f of s plus a instead of f of s. So there, whenever the function was sine omega t, the value was omega by s square plus omega square. So now the result will be omega, numerator remains the same, it is omega divided by s plus a whole square plus omega square. So Utpal, exactly, this is the right answer. Ankita, slightly wrong. Omega plus a, no. Ranjit, that is not the value. Numerator will be changed into omega. So this is the value. I think you all can understand that this is the way in which this exponentially damped function, or the Laplace transformation of exponentially damped functions, can be written. Now again, what will be the value of Laplace transform of t to the power n minus 1 into e to the power minus of at? What is the value of t to the power n minus 1 into e to the power minus of at? Start. I'm waiting. Shikha, the value, I'm telling that the value should be omega, only the omega, because the Laplace transform of sine omega t is also omega by s square plus omega square. Here always you remember that you have to substitute those s by s plus a. Those s by s plus a, not on, and you have to retain all the terms, otherwise you have to retain the terms else here. So only you have to substitute s by s plus a. Now Ananya, please repeat this point. I have already explained. I think you can understand now. So now I am again waiting for you that find out the value of Laplace transform of t to the power n minus 1 e to the power minus of at. 'Papri, is it okay? Papri, is it okay? Ananya, is it okay? Or I have to explain? So now I am waiting for you again to find out the value of Laplace transform of t to the power n minus 1 e to the power minus at. 30 seconds gone. It is Laboni. Laboni, thank you. So Laboni gives the result as Ankita also gives the result. Laboni gives the result as n minus 1 by s to the power. I think you have some problems. N minus 1. So Laboni, it will be I think it will be n minus 1 factorial. Ankita typed it as n minus 1 factorial. Yes, it is n minus 1 factorial, as because the value of t to the power n minus 1 was factorial n minus 1 by s to the power n. So the value, now Ankita, I think uh, yes, Shikha, it is no, what is again you are mistaken the same thing. You have mistaken the same here, that you have to consider the Laplace transform or transformation of t to the power n minus 1. The Laplace transformation of t to the power n minus 1 was factorial n minus 1 divided by s to the power n. Factorial n minus 1 divided by s to the power n. Now, for this function, you have to again just remember that you have to put or you have to substitute s plus a instead of s or in place of s. So earlier the Laplace transformation of t to the power n minus 1 was n minus 1 factorial, it was n minus 1 factorial divided by s to the power n. It was divided by s to the power n. So here actually it will be s plus a whole to the power n, nothing else. It will be, the value is factorial n minus 1. The numerator will remains the same. The numerator will remains the same, as because there were no s related term. Only wherever you find s, you have to put s plus a instead of s. Yes, Shongita, this is the value. This is the value, that the value is factorial n minus 1 divided by s plus a whole to the power n. S plus a whole to the power n. So, okay, fine. Again, thank you to you all. So you are seriously doing problems. Okay, Shikha, thank you. So now I think we have already, we can, I think you all can attempt at least Laplace transformation, right? So now already it is 1 hour and 10 minutes. Okay, I am taking just 10 to 15 minutes more. Actually, there are some properties of Laplace transformation. I think I could derive the formulas, but here the time is constrained, so I'm just mentioned the properties here. So the first property, that is known as the differentiation theorem. This is the first theorem or some important theorems regarding Laplace transform. That is the differentiation theorem. It is the differentiation theorem. Differentiation theorem. So differentiation theorem means here we are going to find out Laplace transformation of some differentiable function. That is, let's find out the Laplace transform of dy dt. Here the function is dy dt. So it is a differentiable function. And if you have to find out this, you have to proceed it as earlier, integral 0 to infinity. This is the function right now, that is dy dt, then e to the power minus st dt. Okay? Now, again, for performing this integration, we have to apply integration by parts again. So, by applying integration by parts, this is the function, first function into now exponential function is written as the first function here. So, the first function e to the power minus st. Now, the integral of the second. So, what will be the integral? Integral of dy dt, as you all know, that it gives me y only. Integral of the second function. Now this is the limit 0 to infinity minus differentiation of the first, differentiation of e to the power minus of st. It gives me minus of s, so it becomes plus e to the power minus st integral, and integral of the second, so it becomes e to the power minus st integral y dt, and here also the limit is 0 to infinity. Now you can see here that s of ys. So here, oh sorry, this will be here, there is a s. So now putting again the values or the limits here, that is, if I put infinity here, it becomes 0, as because I've told you e to the power minus of infinity means 0. And then by putting 0 here, actually I'm getting the value of y0, that is minus of y0. So it here I find that y0, that is putting 0 here, and then plus s. Now this becomes capital Y of s, isn't it? It is actually, whenever I have written integral 0 to infinity e to the power minus st f of t dt, it becomes capital Fs. Now here I have written integral 0 to infinity e to the power minus st y dt, so it means it is actually capital Y of s. So the value becomes s of ys, s of ys, s of ys, yes, s of ys minus y0. Okay, so this is the differentiation theorem of Laplace transformation. Now let's move on to another theorem, and that is, yes, that is the integral theorem. So what is the integral theorem? Now let's move on to an integral theorem. So the differentiation theorem, I've already proved to you. Now the integration theorem. So the integral theorem of Laplace transform of integral 0 to t y dt, integral 0 to t y dt, it gives us the value of 1 by s capital Ys. So it is the value of Ankita have asked that শুধু y লেখা যাবে না. Ankita have asked that why y0 function is written here. if y can be written as instead of y0, no, y, you have to write y0 here. Actually, this is because what I have told you in the initial part of my class, that is Laplace transformation is actually applicable, is actually applied to circuit theory or to network theory. Now, say for instance, there is a circuit which contains a capacitor. There is a circuit which contains a capacitor. You can consider a CR circuit, you can consider a LCR circuit as you wish. Now, here from the physics of capacitor, we know that a capacitor actually stores some charges at the initial stage of the circuit, that if the capacitor is previously used and it was not properly discharged before you are using the same capacitor in a circuit, here you find that there is a chance of some charges residing in the capacitor itself. Now, how you can represent that part of the charge, that amount of the charge, as because you are not actually connecting the circuit, or you are not actually switch on the circuit, or whenever you are switching on the circuit, that is at t equals to 0, actually that capacitor holds some initial charge. Ideally, in any circuit, whenever we are connecting that capacitor in our circuit theory, we actually assumes that initially the capacitor is discharged, but that is not the case practically happened. Whenever in a practical circuit we are going to use a capacitor, it may contain some initial charges in it. So that initial amount of charge is actually can be represented by that y0. Actually, that zero comes from time t0. So whenever if that y0, you are applying that y0 in the circuit which I am discussing, that a CR circuit or a LCR circuit, then you have to tell that that a capacitor, that Q0 or the charge itself, you can discuss it in any way, that Q0 is actually, it may be 0 or it may contain some charge. You have to write that charge. So that is the purpose of using 0 and in y0. Okay, I think I can clear your doubt. So this is our integral theorem, and it gives that Laplace transform of 0 to t y integral of y dt is actually 1 by s capital Ys. Now there are two other, okay, thank you, Ankita. So there are two other theorems as well. The one is initial value theorem. Here again, the term initial value theorem. Initial value theorem. This theorem tells us that if ft and its first derivative, that is f prime t, are Laplace transformable, if ft and its first derivative are Laplace transformable, then f of 0 plus, here I am putting 0 plus, f of 0 plus is actually limit, this is limit t tends to 0 plus f of t. So what is f of 0 plus? It is actually limit t tends to 0 plus the value of f of t. That is, you are just switching on the circuit and at that instant of time, that is the 0 plus time. So that f of 0 plus means it is the limit t tends to 0 plus f of t, and the transformation value is limit s tends to infinity s f of s. As because time and frequency, as you know, they are inversely proportional. So when t tends to 0 plus, it means s tends to infinity, and then the initial value theorem tells us that f of 0 plus is actually equals to limit s tends to infinity s of fs. And last theorem, that is the since there is an initial value theorem, there must exist a final value theorem. That is the final value theorem. You may connect these theorems or the name of these theorems with circuit theory. There are initial value, there are final values in any circuit. So the final value theorem tells that limit t tends to infinity f of t, limit t tends to infinity f of t, actually it will be limit s tends to 0. Again, frequency and time are inversely proportional, so it will be s tends to 0 s of fs. So this is the initial value theorem. So we are calculating time 0 plus, and this is the final value theorem. We are calculating time as t tends to infinity. Both of them, the right hand side value becomes the same, that is s into fs. But remember, when time t tends to 0 plus, the frequency, the limit of the frequency should be s tends to infinity, or when t tends to infinity, s should be 0. So this is all about, in a nutshell. I think this is just a nutshell. I've tried to explain you in a nutshell about Laplace transformation. I'm actually tried to explain you the theorem itself, how you can or how we can derive Laplace transformations of some important or some famous functions, familiar functions, and but what I can't explain here right now, as well as it is also not in the syllabus of your circuit or your mathematical physics, that how we can apply this Laplace transformation in our circuit theory part. So here, this is all about Laplace transformation. We have no time right now. Your exam, your internal exam is right now on Saturday and Sunday, so there are no time to discuss about matrix. I think after the exam is over, in the next week, again we are continued our classes, and then some quantum mechanical classes will be there, some mathematical physics classes. I can discuss, if you require, obviously if you require class about matrix, I can discuss about matrix. I think some digital circuits classes are also required, as well as electronics, analog electronics classes are not at all here. So these all classes are going to happen if you needed this, obviously. So just now, right from me, best of wishes for your internal exam. Okay, Shikha, yes, Shikha, you have rightly pointed out that no, this cannot be done. Ujjwal Kumar Rai, this cannot be done. I can't send internal exam links to your email ID. I can't send. I am going to send the questions or the Google Forms in the group, in the WhatsApp group. I can't send any individual of you or in your individual email ID. I'm helpless. Okay? Till now, goodbye.